Thank you. Hi, everybody. Can you hear me okay? All right. So welcome to this talk. We'll talk about noisy neighbors. And I want to start with this. If you haven't seen this, you should watch it. There's a link. Uh, Search it on YouTube. It's called Positive Affirmations for Site Reliability Engineers. So it starts like this. It's night. There's a lone SRE at their desk. There's a lone SRE at their desk. He's seeing the errors in production, the rising cost of the deployment, and he's just feeling so frustrated and haggard. He meditates. A calm female voice tells him, "Your pipeline is green. Your tests are well written and stable. Your friends and family understand what you do. You were born to deploy Kubernetes clusters." And so watch the whole video. But this got me thinking, why do we choose to operate these complex deployments and just spend all our time and effort in making them work? And for me, the ultimate affirmation is this. Your deployment is highly available and cost efficient. Users delight in the product and its performance. And this is the holy grail, right? Like, this is what we're trying to accomplish. And companies understand that performance matters. You might know this study by Amazon, released a few years ago, where they found that for every 100 milliseconds of added latency, they lose 1% of revenue. This result has been reaffirmed over and over in the past few years. It really matters for the bottom line of companies to have good performance. And I especially like this case study by Rakuten24, which is a Japanese online grocery. They ran an A/B test with two versions of their applications that were identical functionally, but only had performance improvements. The faster version was 400 milliseconds faster. And they found amazing results with this A/B test. They found 53%, a 53% increase in revenue per visitor, and 35% decrease in bounce rates, which is amazing just for 400 milliseconds. But with that, users also expect better functionality. So your deployments might not be as complex as these extreme examples of service maps, but still users expect more and more functionality from their deployments, right? Like, they want better recommendation engines, they want search, they want maybe AI, and generally just a better experience. And with that richer experience comes complexity. And as you have more complexity, it also becomes harder to reason about performance. And when performance degrades, it's easy to just blame complexity, right? Like the spaghetti monster of complexity, or it's the network, right? But a lot of this performance degradation really comes from just plain old congestion for resources happening on the machine that we just have no visibility into. It's just simple as that. And so what if I told you that a small group, a small cabal of engineers got together at some of our favorite hyperscalers and solved this problem, and were able to build a resource allocation system that enabled them to run 50% more transactions on the same hardware and reduce the latency to users by factors, or 5x, 15, 14 times, right? It would be amazing, right? How could we not know about this? How can they have it and the general community not? Well, it turns out that the hyperscalers actually developed these features, but not in secret. They published many papers, dozens of papers over the last decade and a half, from well-known universities and your big hyperscalers. And it just hasn't reached common practice for the rest of us. And I think there's enough there today to build general purpose resource allocation systems for the Kubernetes community. And this is the subject of this talk. So in this talk, I want to explain what is memory noisy neighbor. Should we care? Does it really impact our users or not? What can we do to solve this? And to talk about our open source efforts. I did my PhD in noisy neighbor mitigation, specifically network noisy neighbor. I then started a company to do network observability using eBPF, which we sold to Splunk. And I'm now still a maintainer on the OpenTelemetry network collector, which we contributed. And now I'm working on noisy neighbor mitigation. Okay, so what is noisy neighbor, and specifically memory? Well, let's start with what is noisy neighbor in general. We run cloud-native apps, and ultimately those applications run on physical servers. You still can't hear me well? All right. How about this? Oh my, I can hear myself better this way. So I'm not going to start from the beginning, though. Let's continue from here. So what is noisy neighbor? So our cloud-native applications actually run on physical hardware. And they have to share finite hardware resources that the servers provide. In noisy neighbor, you have one application that is using a lot more than its fair share. And so the other applications cannot get those hardware resources and their performance degrades. And in this talk, I'm going to focus on these two resources of the memory subsystem, the last level cache, and which I'm just going to call cache, and memory bandwidth. So how does cache noisy neighbor look like? Usually, our application's memory fits into the memory hierarchy of the hardware like this. You have the blazing hot set, working set in L1 cache, and then the hot, warm, and cool working sets in L2, L3, and DRAM. When a noisy neighbor comes in, it uses the L3 cache very aggressively, which is shared among all of the cores on the physical CPU, and evicts your application out of the L3 cache. So now your application, instead of going to L3 cache, which is fast, has to go for DRAM for the warm working set. In the more extreme example, the noisy neighbor lives on the hyperthread next to your workload and uses the L2 cache very aggressively and evicts your application. So now your application needs to go to DRAM even for the hot working set that it uses quite a lot. And the performance difference is massive. It could be 50 times or more to load data from DRAM versus L2 cache. And so you can see here that in theory, your applications would run a lot slower if they have memory noisy neighbor. And it turns out that in practice, they actually tend to run slower as well. This is a case study that Google published a few years ago, where they ran their production workloads with synthetic load generators. So you can see web search here is the Google search node. ML cluster is a machine learning text classification system that handles user traffic. It's interactive. And memkeyval is an in-memory key value store like memcache. And they found that in face of memory noisy neighbor, these applications experienced slowdowns of 5 times for web search, 5 times for ML cluster, and up to 14 times for memkeyval. So there is dramatic slowdown in practice. So I want to run a short survey. 2 groups. If you know of a production cluster with user-facing traffic, Do you only use the bare metal machines or machines that only have full CPUs? Raise your hand. Practically, nobody. Somebody who knows and uses any type of machines, the smaller ones, the 4 core, the 8 cores, the 16 cores. Well, not a big sample size. Oh yeah, we have some hands here. So, uh, you know, practically everybody uses some small machines. And so think about this. Best practice today is to separate our big data workloads from our interactive workloads, right? Because we don't want somebody to run a big data job and just ruin the performance for our interactive workloads, user-facing workloads, right? So we separate those clusters. But if you're running in the cloud and you're running on the smaller VMs, then what is actually happening looks more like this. You're running on VMs, and there are other VMs running next to your VMs that are from random folks on the internet. Some random dude is running workloads next to your VMs, and probably some batch. And so while you've done all the work to separate your own big data analytics from your interactive clusters, you're actually running next to some random guy's analytics clusters. So yeah, this is fine. The question you might ask is, do cloud providers protect our workloads, our VMs, from neighboring VMs, from memory noisy neighbor? And the answer is no. I've talked to several cloud providers, and it seems like there's no such protection today. And so think how absurd this is. We have engineers who spend months and years of their lives optimizing deployments. They might add database indices. They might change the data schemas in the database so that the queries run faster. Might break up large services into small services so they can transactions can process in parallel, or just plain old profiling and fixing bottlenecks. But even with all this work, you can have a noisy neighbor running on a neighboring node that just obliterates performance for your compute infrastructure. How terrible is that? And so first takeaway is, if you are running more than, let's say, 1,000 cores, you should prefer the bare metal machines to a few bare metal machines to a lot of the 4-core, 8-core machines. Because then at least you know who are your neighbors, right? It's your own workloads that is interactive, that is a lot better behaved than the batch workloads of some random organization. So the next question is, let's say I don't have big data analytics running on my cluster. I only have interactive workloads. Am I going to experience noisy neighbor? And the answer is yes. In this experiment by MIT researchers, they ran memcache alongside a garbage collected workload. So you can see as the experiment starts, memory bandwidth is low. But when the mark phase of the garbage collector begins, suddenly the memory bandwidth saturates. If you look at latency, it is steady at 50 microseconds, 99.9th percentile latency. But as the mark phase begins, it jumps 3 orders of magnitude, 1,000 times, due to the saturation in memory bandwidth. So you don't need big data analytics jobs running alongside you to experience noisy neighbor. Garbage collection could be noisy neighbor, video streaming, and even if you have a service that once in every 1,000 transactions has a big transactions where it has to touch a lot of rows in the database, that could be noisy neighbor. So should we care? You might know one of these surveys. This was published by Datadog, showing that a large majority of the containers that we run use a lot less CPU than what we request for them. So there's a lot of waste in our clusters. And I ask people, how much is your CPU utilization usually? And they tell me usually between 20 and 40%. And actually, that is was a pretty good number. You have the big companies publish their CPU utilization a few years ago, and they were between 20 and 40%. So all sounds reasonable, except that a few years ago we had a new batch of results with a lot better CPU utilization. For example, Google went from 35% to 50% between the years of 2011 to 2019. So that is 1.5 times more that they're getting out of their machines, right? Like between 35 and 50%. 50% more workload. So what happened? I was able to find at least 2 major contributors that contributed to that they published. One is advancements in vertical autoscaling. So Google has systems to choose the memory and CPU requests and limits dynamically for the workloads, and we have some companies doing that for Kubernetes workloads as well. And the other contributor is handling of noisy neighbor that enables them to run at this increased density without degrading user performance. And this is what I'm going to talk about. So just to illustrate why we should care, take a look at these 2 simulated systems, right? A system at high load that has a lot of these memory saturation events because of garbage collection, and a system at low load that has fewer of them. And if you think about P95 or P99 latency, which one is going to have better P95, P99, right? Like the low load, because you have these events, the high load events degrade your P95, P99. And so we've been programmed when we see high P95, high P99 to decrease load on the system, right? We scale out in order to solve high tail latency. Let me say it a different way. We have high load, which causes memory contention. So CPU efficiency degrades because we've seen now you evict, the noisy neighbors evict your applications out of cache. So the CPU has to go to slower memory. And so application service times degrade and we hit our SLO limits. And what we do is we scale out as a solution. And I want to claim that this is an anti-pattern. We shouldn't do this. It's wasteful and ineffective because we're just creating these systems at low utilization and we're not tackling the root cause of the problem. Instead, we should tackle memory contention and make sure that these saturation events don't degrade latency. And so if we can do this, we can run at higher density without degrading user performance, so we can reduce cost, just scale down our systems and keep good SLAs. We can allow our developers to build more features without first optimizing their code to make sure that they fit within the P95 SLAs. And we can just roll it to users and increase their, improve their experience. And so, if the hyperscalers have it, why shouldn't we? This gets us a lot closer to our holy grail, right? Like it tackles both cost efficiency, product features, and performance. So what can we do to actually mitigate noisy neighbor? There are kind of the, we alluded to 2 types of memory noisy neighbor that we can have in our systems. One of them is external from external VMs. And that we can solve. We talked about running on bigger VMs that don't have neighbors, right? Like if you don't have neighbors, you eliminate this type of noisy neighbor. Another idea is to detect when your VM has noisy neighbors next to it. Run some tests when you spin up the machine or every few minutes. And if you find that you have a noisy neighbor, if you're on the cloud, spin up a new VM, turn this one off, and you have a better experience for users. And if you're excited about that avenue, please reach out to me afterwards because we're thinking about how to do this. Another one is the noise between our own workloads, and there we what you can do is if you find an application that is structurally always noisy neighbor, for example, it allocates and frees a lot of memory to process user requests, so it triggers a lot of garbage collection. It affects everybody's tail latencies, the P95 and P99. So if we find 1 out of 20 workloads that does this, let's isolate them to their own node pool. And now they do damage to themselves, but not to everybody else. And you can increase SLOs for everybody. Another thing is if you had visibility into which workload is noisy neighbor, you can work with the developers. Just don't allocate and free so much memory. There are things they can do to reduce that load. And an exciting opportunity is to limit the noisy neighbors. Because modern CPUs have mechanisms where the operating system can specify how much cache and how much memory bandwidth each application can use. And even if you don't have support in your CPUs, many CPUs do, but even if you don't, then you can do other things like putting the offending workloads on their own cores and then reducing the frequency of these cores. So you limit the amount of damage that those noisy neighbors can do inside your workloads. And so I get this question a lot. Shouldn't containers do this? Wouldn't containers already contain applications? Well, they don't. Containers more deal with security and with delivery of software and performance. We just haven't implemented that yet. But the kernel has a mechanism to control these cache allocations and memory bandwidth, cache and memory bandwidth allocations using the resource control subsystem in sysfs. So what we can do is we can find applications using more than their fair share and limit them, put them in these sandboxes where they can only evict a fraction of the cache. And in fact, Google published in 2013 that they have a system like that in their clusters. And Alibaba in 2020 published that they had a system running on an order of 1 million cores for over 2 years. So we can do this. The problem with these systems is that they measure memory events over long periods of times with a lot of aggregation. So look here on these two graphs. We simulated these two graphs, one at 10 millisecond granularity measurements and one at 1 second granularity aggregations. And you can see that the 1 second aggregation, you lose all of the information. And so the systems by Google and Alibaba have to collect massive amounts of data over hours in order to make decisions, which doesn't work for garbage collection that happens every, it takes a millisecond to 100 milliseconds. And so we set out to build a collector that measures memory bandwidth at 1 millisecond granularity. And so let me show you some of the early results. We took the OpenTelemetry demo, which is what you'd see at a lot of the observability vendors. And we scale, and it's good because it runs in a lot of languages. And we scaled it up from 10 users to 10,000 users. You can see here the number of requests per second increase as this experiment progresses. And you can see the median P95 and P99 latencies. And we were able to measure 1 millisecond samples of memory bandwidth. And so there's less than 24 people who've seen this before, so you're kind of the first big audience to see this. Here is one of the measurements from that run. And you can see that memory bandwidth is very variable in this measurement, right? So it makes sense that, that it matters, right? Like we have enough variability that we can find what's, the bad behaviors. But I'm not sure how general these measurements are, because here is a CPU graph over the 4 minutes that we run the experiment, and the front end takes more than half of the CPU cycles. So I have reason to believe that this is not the this doesn't generalize very well. So what I'd like to ask everybody here is if I'll just here. if you want to see how your cluster behaves, come and talk to us. We'd love to work with you to understand your noisy neighbor behavior, and it will help us develop algorithms to detect noisy neighbor. Right, like right now we need to know, is the system just churning along nicely, or is there actual contention that degrades performance? And it's a very powerful way to help right now. And if you want to contribute, join the project, please reach out. So I hope this will help us get to our holy grail and closer to the efficiency that the major players have. So thank you. I'll be around if you have questions.